Let's find the derivative of the function f of x is equal to x minus 3 whole cubed. First, we'll expand the expression using the binomial expansion and then find the derivative of each term. Therefore, the derivative of f of x with respect to x is equal to 3 into x squared minus 6x plus 9. However, differentiating such functions with higher powers is quite tedious. For example, how will you find the derivative of x minus 3 whole raised to the power 50? Such functions can be differentiated by using the chain rule. F is a real-valued function, which is a composite of two functions, u and v. Suppose t is equal to v of x, and if both dt by dx and du by dt exist, then df by dx is equal to du by dt into dt by dx. The chain rule can be also applied to functions that are composites of more than two functions. That is, if f is a real-valued function which is a composite of three functions u, v, and w, then the derivative of function f is as shown here. Now, let's apply the chain rule to differentiate f of x is equal to x minus 3 whole raised to the power 50 with respect to x. Clearly, function f is a composite function. Let's define the function as h circle g of x, where g of x is equal to x minus 3 and h of x is equal to x raised to the power 50. Suppose t is equal to x minus 3. This implies that f of x is equal to h of t, which is equal to t raised to the power 50. By the chain rule, the derivative of f with respect to x is equal to the derivative of h with respect to t into the derivative of t with respect to x. Thus, df by dx is equal to 50 into t raised to the power 49. On substituting the value of t, we get the derivative of f of x with respect to x is equal to 50 into x minus 3 whole raised to the power 49. Let's now find the derivative of another function. F of x is equal to sine x squared plus 1 by using the chain rule. Clearly, f of x is a composite function involving a trigonometric function and an algebraic function. Let's define the function as h circle g of x, where g of x is equal to x squared plus 1 and h of x is equal to sine x. Suppose t is equal to x squared plus 1. This implies that f of x is equal to h of t, which is equal to sine t. So, the derivative of f of x with respect to x is equal to dh by dt into dt by dx. On differentiating, we get 2x into cos t. On substituting the value of t, we get the derivative of f of x is equal to 2x into cos of x squared plus 1. Alternatively, its derivative can also be obtained by finding it directly. That is, on differentiating both the sides with respect to x, we get df by dx is equal to d by dx of sine of x squared plus 1. Now, by the chain rule, we get cos of x squared plus 1 into d by dx of x squared plus 1. The derivative of x squared plus 1 with respect to x is equal to 2x. Hence, the derivative of the given function is equal to 2x into cos of x squared plus 1. Let's now learn to differentiate functions involving two variables. Consider the equations y minus 2x is equal to 5 and y plus cos y is equal to sin x. Let's analyze each equation. The first equation can be solved for y and rewritten as y is equal to 2x plus 5. Such an expression, which can be easily solved for y and written in the form y is equal to f of x, is said to be y is given as an explicit function of x. However, for the second equation, we do not see any easy way to solve it. Clearly, it is inherent that y is a function of x. Mathematically, a function that is formed implicitly is called an implicit function. Let's first find the derivative of y minus 2x is equal to 5. First, we'll express the equation as y is equal to 2x plus 5. The derivative of y with respect to x is equal to 2. Alternatively, we can also differentiate the equation with respect to x on both the sides. Thus, we have d by dx of y minus 2x is equal to d by dx of 5. We know that the derivative of a constant is 0. Now, by the property of derivatives, we get dy by dx minus d by dx of 2x is equal to 0. This implies that dy by dx minus 2 is equal to 0. Therefore, dy by dx is equal to 2. Next, let's differentiate the equation y plus cos y is equal to sin x. Such equations can be differentiated directly with respect to x. Differentiating both the sides with respect to x, we get d by dx of y plus cos y is equal to d by dx of sin x. By applying the property of derivatives, we get d by dx of y plus d by dx of cos y is equal to d by dx of sin x. By the chain rule, the derivative cos y with respect to x is minus sin y into dy by dx, and the derivative of sin x with respect to x is cos x. Taking dy by dx common, we get 1 minus sin y into dy by dx is equal to cos x. Therefore, dy by dx is equal to cos x divided by 1 minus sin y. Now, let's find the derivatives of inverse trigonometric functions. Beginning with the function f of x is equal to sine inverse x. Let y be equal to sine inverse x. This can also be written as x is equal to sine y. Let this be equation 1. Now, let's differentiate both the sides with respect to x. Using the chain rule, the derivative of sine y with respect to x is equal to cos y into dy by dx. This implies that dy by dx is equal to 1 divided by cos y. Let's write cos y is equal to the square root of 1 minus sine squared y. On replacing sine y with x, we get 1 divided by the square root of 1 minus x squared. Therefore, dy by dx is equal to 1 divided by the square root of 1 minus x squared. The derivative of sine inverse x is only possible in the open interval -1 and 1. Next, let us find the derivative of f of x is equal to cos inverse x. Let y be equal to cos inverse x. This can also be written as x is equal to cos y. Let this be equation 1. Now, let's differentiate both the sides with respect to x. We know that the derivative of cos y with respect to x is equal to minus sine y into dy by dx. This implies that dy by dx is equal to minus 1 divided by sine y. Let's write sine y is equal to the square root of 1 minus cos squared y. On replacing cos y with x, we get minus 1 divided by the square root of 1 minus x squared. Therefore, dy by dx is equal to minus 1 divided by the square root of 1 minus x squared. The derivative of cos inverse x exists only in the open interval -1 and 1. Now, consider the function f of x is equal to tan inverse x. Let y be equal to tan inverse x. This can also be written as x is equal to tan y. Let this be equation 1. Now, let's differentiate both the sides with respect to x. We know that the derivative of tan y with respect to x is equal to sec squared y into dy by dx. This implies that dy by dx is equal to 1 divided by sec squared y. Let's write sec squared y is equal to 1 plus tan squared y. On replacing tan y with x, we get 1 divided by 1 plus x squared. Therefore, dy by dx is equal to 1 divided by 1 plus x squared. The derivative of tan inverse x exists for all real values of x. In a similar manner, we can determine the derivative of cot inverse x. Sec inverse x and cosec inverse x.